While we're on the subject of the typing system, we should revisit this feature, which we should recall from C. So this is a feature that C has as well, although we don't use it as much in C as we do in C++, and we're going to use it a whole ton in C++. It is the const specifier. It is a way of creating the rather oddly named constant variable, a variable that is constant, that cannot be modified, which of course seems like a contradiction in terms, but is actually pretty useful. Because, for example, as you saw in 111, there are cases where we have some magic number, like pi, we want to use over and over again in our program, but we want to use it with a name. We want to give it a name and have it participate in the program just like any other variable with a name and a type. And we don't want to modify it because there's no context where I'd want to modify the value of pi. So if I did it by accident, I could break something. So it's useful to have a feature that prevents a variable from being modified. So I've drawn a nice extra wide box for the comfort of this large numerical value, and it is a float. Its name is pi, but it has the added restriction of being constant. And that means I can use it like any other variable. It's in the scope of main. It can be used like any variable in main, except that any modification is forbidden. So I'll compile this as it's written, and we can see it gives a warning about never using it. But notice that besides those two warnings, everything checks out. If I try and modify the value of pi, though, it gives me a compile error. And that's great because obviously I can't imagine a case where that wouldn't be an error. And as I mentioned in a previous video, compile errors are great because if there's something wrong with my code, it's great for the compiler to find it instead of for me to have to go find it. And so that's the use of the const keyword you're probably familiar with from C. And frankly, I mean, it may well have been that in all of 111, you only ever used const for like storing the value of pi. But that's all about to change because we're going to need it a lot in C++. So down here, I'm going to comment out pi here so we stop getting that warning about unused variable. Here I have a variable called x. And x is an int. And we'll of course notice that in these print statements I'm about to uncomment, I want to also use a variable called y. And I'm going to create a variable called y. I suppose I could create a reference to x. So that means that at the moment we have two names for the same variable. So we've got x, it's initialized to the value 6. I've got y, which is another name for x, and then I print them both out, and in the middle I modify using the name x. But of course we know by now that if I modify x, I'm actually modifying this box, which is also y. So I should expect the modification is reflected in both. And sure enough, it is. So both are equal to 6, then I set x to 10, and both are equal to 10. But one interesting thing you can do in C++ is when you create a reference to something, you can impose restrictions on that reference. So I could decide that y is a reference to x. Y is a name for the same thing as x, but y, the name y, is constant. So I'm allowed to use the value of y. I can use y to refer to the contents of the box, but I'm never allowed to modify those contents using the name y. The name x has no restrictions. So in this case, I'm allowed to read from the name y, where I read from this box. I'm allowed to modify using the name x, but I'm not allowed to modify using the name y. So we'll see this compiles and it still runs. Whereas if I change this to be modifying the value using the name y is a constant reference. And therefore, I get this compile error. You can't assign to a read-only reference. You can only read its value. Okay, so this allows us to create references that are restricted, that are read-only. And so they both names refer to the same box, but if I use the name y, I'm not allowed to write anything. I'm only allowed to look inside. And I'll just restore this to the way it was so that it compiles again. And one other note, the position of the const specifier is actually up to you. You can choose to put it before the underlying type, so I could write const int, or I can write this. I actually go back and forth. It depends on what I'm using it for, but you will find that in this course, I often put the word const, when I'm referring to constant references, I like to put it right next to the ampersand, and then I read this as integer const reference. By putting the word const there, at least for me, it's a matter of personal taste, but it helps me remember that it's a reference to something that I am making a constant. So y would not otherwise be a constant, but I'm adding that restriction to it. I'm forcing y to be a read-only name for that variable. So it is up to you whether to put const before or after the word int, and even I am not perfectly consistent, but these days my preference is to put it after the underlying type. Okay, so then the question is, why do we care? I mean, as usual, this is a contrived example. Why do I even want to give two names to a variable inside a function? Why would I want to make one of them read-only? That doesn't make any sense. And as usual, the reason I care is not because of this example, but because of throwing data around the program. References are very useful, and I often want to pass data by reference because I want to avoid, for example, making a copy of the data. But I know that passing data by reference invites a certain risk, which is if I give somebody my original, they might modify it. Maybe they don't mean to, but they could do it by accident. So it'd be great if I could find a way of preventing the modifications that I don't want to happen. So I have this code here. In this code, we have the print vector function, and notice that the print vector function accepts the argument vector by constant reference. The print vector functions we've seen so far have looked sort of like this, where it accepts the vector by value. Now, if it accepts the vector by value, then what it gets is a copy, which means if it modifies it, there's no harm done because the modification is only to the copy. The problem is if I'm printing a vector of 1 billion elements, making that copy might take a very long time. So there is a benefit, even when I'm printing a vector, there's a benefit to passing in the original. But I want to pass the original in with some restrictions. I know that no reasonable print vector function should ever need to modify the vector. So what I'll do is I'll pass the vector by constant reference. I give it the original vector, but I put the vector in a glass box so you can look but not touch. Now, obviously, I wouldn't have intended to write a broken print vector function that modifies the vector. But if I force the input to be constant, it means that I can't accidentally modify the vector either. It's always going to be read-only. And this course will see lots of cases where if we don't need to modify what we're taking in, why not take it by constant reference? That saves the copy. I don't have to make any copies to do it, but it also prevents unnecessary modifications. And so it means I can trust the function more to not modify my original. Okay, so down here in main, I create my vector v, and I create another variable called vc, which is the same thing. So it's a reference to v. So both v and vc, but vc is constant, refer to the same vector, which is the element 6, then 10, then 17. And remember, just like here, you'll notice on line 19, I write const vector ampersand, and on line 9, I write vector const ampersand. Those are equivalent. You can use either. As I said, this actually is my preference these days, is to put const before the ampersand. So I guess I'll fix that up. But remember, if you see either notation, both are correct. There are cases where the position of the word const can make a difference, so whether you put it after the ampersand can be a thing. We're not going to see any in this course where it's that big of a deal, but for now, a const can come either right before the ampersand or before the underlying type. So here, when I create the reference vc, that means I'm referring to the same vector as v refers to, but I'm not allowed to use the name vc for any operation that would modify the vector. And that means anything that modifies an element of the vector or modifies the size of the vector, any modification is now forbidden. So I'm allowed to, for example, create this reference vc and then modify v, because v is the original vector, it is not read-only. And so what I should notice here is that when I perform this modification on line number 21, it modifies index 1 to be 187. So index 1 is this. I'll modify this to be 187. And when I print them out, because both v and vc are in fact exactly the same vector, it prints the same thing twice. I just print both vectors. I'm allowed to call print vector with vc because vc is a constant reference, and so is what print vector takes in. In general, you cannot convert a constant reference back to a non-constant one and still, obey best practices. You can't in good style do that. C++, even though creating a constant reference is like wrapping up your vector in a glass box so you can look but not touch, C++ does actually provide a variety of tools for breaking open glass boxes, although we shouldn't generally find ourselves using them. So once I create a constant reference, I should assume vc can never be modified in any way. If I try modifying it, so if I do vc.at2 equals 100, then I'm going to get a compile error, because doing that would modify vc, and vc is constant, so I'm not allowed to. And so that's good, because the point of vc is that it's a constant reference, that it's read-only, and we can see the compiler prevents that. Now, to be clear, there's nothing wrong with using .add. I could use .at to view an element as long as I don't try to modify it. It's only operations that result in a modification that are forbidden. So we can see here, it does print out element 2 because I'm not trying to modify. If I were, that would be a compile error. And so this gives us the freedom to now pass our original data around the program, but protect it with this const specifier so that we get all the benefits of passing the original without any of the risks associated with other functions or other parts of the program modifying my original data.